We will begin. Hello, everybody. Can you hear me?
Yes, so.
All right. Okay. Um, I'm gonna clear my throat every now and then. I had a head cold and it's not going away very easily. In any event, today our lecture will be on regression analysis, and we are gonna begin with simple linear regression. Now, I'm going to conduct this lecture by pulling up some PowerPoint slides, which hopefully I will remember to upload into YouTube, so you can watch it again if you so desire. I'm going to go through this PowerPoint slide to explain what we mean by regression analysis. Very simply, all along, we have been looking statistically at a single variable. For example, the average age of children, the average living amount of living space in a house, and the average age of houses, or the average output of a machine, single variable at a time. And even though we have tested hypotheses with the single variables, we have actually had variations of the hypothesis testing for one population, testing for two populations, and testing for three populations, but it's always one variable. Today and next week, we are going to talk about two variables or more variables, two or more variables. And we're going to look at testing hypotheses about the relationship between two or more variables. And so this is what we call regression analysis. Now, I'm going to pull up a slide so that I can go through the process. All right. So this is our slide. Can you all see it? Hello?
Yes.
Okay. You can see it. Okay. So today we're going to talk about simple linear regression. And simple linear regression is just the beginning of regression analysis because then we go into multiple regression, and we will stop it at multiple regression analysis. There are different ways of doing regression analysis. There's nonlinear regression. There are different forms of multiple linear regression. Simultaneous equation regression. There's also seemingly unrelated regression. So now we're going to begin from simple linear regression, okay? And in simple linear regression, you are assuming that there is a linear relationship between two variables. So this is why I call it simple. We're looking at just two variables for now. Next week, we're going to look at multiple variables. So we assume there's a linear relationship, not a nonlinear relationship, a linear relationship between two variables. One of the variables is called a dependent variable, and the other variable is called the independent variable. So let's look first at our objective, our learner objective, is that once you look at the relationship between two variables, one which is a dependent variable, the other is an independent variable, we are simply saying that the values of the dependent variable depend on the values of the independent variable. And very, very simple. Let us look at, say, the amount of money that a family spends on food. The amount of money that a family spends on food will depend on the size of the family. So that's a linear relationship between two variables. The amount of money that is spent on food is a dependent variable, and the values or the amount of money spent on food, which we call the values, dependent variable, depend on the size of the family, which we now call the independent variable. So we're going to apply the methods of regression analysis to estimate the linear relationship between, say, the amount of food that the family spends and the size of the family. So if there's one person in the family, they will spend less money. If there are two persons, there are 3, 4, 5, and 6. And so we assume a linear relationship between those two variables. Now, we would also evaluate the significance of the slope of a regression equation. What does that mean? Suppose that we say there is a linear relationship between the amount of money that a family spends on food and the size of the family. We want to ask ourselves a very simple question. Does the size of the family significantly affect the amount of money a family spends? That is a question. That's a hypothesis to be tested there. Because when you put together any two variables and try to estimate a relationship between them, you might actually find some kind of number. But the question is there really a significant relationship between the two variables? And we will explain that as we go. And then we will use our estimate to evaluate, to predict. For example, once we estimate the relationship between the amount of money that the family spends on food and the family size, then we can estimate, suppose you have 7 people in a family, how much money will they spend on food? Suppose you have 4 people, how much money will they spend on food? So that is how we use our regression equation to predict, to make predictions about the dependent variable. So, as I've been explaining, our objective here is to evaluate the relationship between two variables, and we will call them y and x. The dependent variable will be y, the independent variable will be x. And the first thing that we estimate is the nature of the relationship. Is it a negative one or a positive relationship, or is there none? Do we have a negative relationship or a positive relationship? For example, the relationship between quantity demanded of a good and the price of the good is a negative one. The relationship between the price of a good and the quantity supplied is a positive one, okay? All right, so once we ask ourselves the nature of the relationship, then the question is, what is the size of the relationship? For example, we think about, say, consumption. Now, consumption expenditure of an individual depends. Please mute yourself so that you do not interfere with the, we don't create echoes in the background. For example, consumption expenditure depends on income, okay? The question is, for each additional dollar of income, how much is spent on consumption, okay? So for me, it would be I spend, for every dollar increase in my income, I will spend 20 cents on consumption. For somebody else, it might be 70 cents. For one community, for one country, it depends on what you want to estimate, okay? For one city, it could be 10 cents. For another, it could be 20 cents, okay? Then, lastly, we ask ourselves, how strong is the relationship between the two variables? Which is to say, what percentage of changes in the dependent variables is explained by changes in the independent variable, okay? What percentage of changes in the dependent variable is explained by changes in the independent variable? These are the things we're going to look at. So then what is it that we are really talking about? What is the form of a regression model? And in fact, let us first begin by explaining the background to what we call a regression model. Now, a regression model is nothing but the standard linear model that many of us know. Y is equal to A plus BX. That is the standard model, okay? That is standard linear model. That is to say, Y, the dependent variable, is equal to A, and A is a constant value, plus B times X. And so B is the rate of change, or the slope of the equation. B is a rate of change, or the slope of the equation, and A is the constant value. Okay, I'm going to all right. So, for example, there is a model that says that Y is equal to 10 plus 5 times X. Okay, Y is equal to 10 plus 5X. This is a simple function, very basic linear function. And so the constant value is 10, and the rate of change is 5. We all know that from basic algebra. And so I use that as an example. Y is equal to A plus BX, and we model it here. Y is equal to 10 plus 5X. And so, as you can see here, we create a table before we make a graph. When X is 0, Y is equal to 10, which is the constant. When X is 1, Y is equal to 15, and so dy dx is equal to 5, okay? So the rate of change is 5. As you can see, the rate of change is equal to 5. Now, we can look at a different model, okay? We can look at a different model. Now, this is a model of a negative relationship, okay? It's a model of a negative relationship where Y is equal to 25 minus 2x, okay? Again, here we have a negative relationship because the rate of change is negative, minus 2, okay? dy dx is minus 2. So when you plot that on a chart, what do you have? That's a negative relationship. Now, what is it that you observe about these two equations? Now, what you see is that when you know X, you know exactly what Y will be, because Y is 25 minus 2X. We know exactly that when X changes by 1, Y will change by dy dx, which is minus 2 in this case. And when we know the value of X, we know exactly what the value of Y would be. As you can see, when you plot the graph of the equation, you have a perfect relationship between Y and X. You have exactly a straight line that joins all the dots without missing anything. Okay. So that is the simple equation of a line. And this is what we are trying to do with regression analysis. We want to find the equation of a line. That is what we are trying to find, the equation of a line. Okay, so in regression analysis, we assume a linear relationship between, for example, the size of a home measured in square feet and the cost of the home, or the price of the home. So that is what we're trying to do in regression analysis. Here, we assume a linear relationship between, say, the size of a home measured in square feet and the cost to heat the home, say, in January. How does the cost vary relative to the size? So we specify a model. C is a function of the size of the home. And so now, what is it then that makes regression analysis different? What is it that makes regression analysis different? Now, as you can see here, I say enter the imperfection. Okay. Now, the difference between a regression model and the simple linear model that you see there is that the relationship between X and Y is perfect. While in regression, what we observe from data is that the relationship is not perfect, but there is a tendency, okay? There's a tendency, a direction that is easily observable. And that is what we are looking at, okay? For example, you look at this model, look at the data here. All right, so you can see here, this is a model of sales versus sale calls. Now, think about a salesperson, or you think about salespersons. Here we simply saying that dollar sales is a function of calls, okay? So we are saying that for a salesperson, the more calls they make, the more sales they generate. That is to say, is there a linear relationship between the amount of sales and the number of calls? As you can see from this chart here, you can see truly there is a linear relationship, a linear correlation, a positive one between sales calls and the amount of sales that are made. You can see there's a tendency, but the relationship is not exactly perfect. The relationship is not exactly perfect. For example, you can draw a line in the middle of that, okay? Can draw a line right there in the middle, which shows that there is a positive relationship. Are you seeing my lines? Hello? Can I hear somebody? Unmute yourself.
Yes.
Okay. You can see the line that I was drawing. Okay, all right. So you can see the relationship is not perfect, but you can see there's a tendency that the more sales calls, the more copiers that are sold. And so our objective in regression analysis is to draw a line perfectly in the middle of these scatter plots, okay? That is what we are trying to achieve. We want to draw a line in the middle of the scatter plots. And in doing so, we are only providing an estimate of the relationship between sales calls and the number of copiers that are sold. All right, so now how do we proceed to do that? I'm going to show you exactly all right, so this is where the data comes from. This is the data on sales calls and copiers. If you plot this data on a chart, what you will see is that a tendency, a positive tendency for calls and copiers sold. The more calls a salesperson makes, the more copiers they sell. And our objective is to estimate that relationship. So how do we go about that? Okay. Now, when we specify a regression model, we specify then that y is equal to a plus b times x plus e, where e acknowledges that there's going to be some error in our estimation of a and b. Okay. Now, for example, in our model, when we say the number of calls okay, as a function of a times bx, I'm sorry, the number of sales, not calls, okay, it's a function of a times bx, calls. What are we trying to say? All right, so now a is the constant value, all right? So if x is 0, some sales will be made. And we're saying that we estimate that if a salesperson makes no calls at all, they're going to be able to sell something anyway, okay? And so the amount of sales will be A. Okay, but what is A? We don't know the value of A. We don't know the value of B. We are trying to estimate the value of A and the value of B, okay? And so we estimate A using A hat, and we estimate B using B hat. That is our objective. We're going to estimate A, we're going to estimate B. But the estimates were called A hat and B hat. Those are the equivalent of X bar, which is the sample mean. In order to do that, in order to provide our estimates, we use the formula, and this is what we call the ordinary least squares method. So we use the formula for B hat, okay? That is the formula for B hat. And that is the formula for A hat. All right. So now, as you can look at the formulas, when you look at these formulas, you see that in order to estimate B hat or A hat, you have to find the mean of X, the independent variable, and also the mean of Y, the dependent variable. You have to find their means, okay? You have to find their means, and you use them to estimate B hat and to estimate A hat. So how do we then proceed? I'm going to provide you an illustration. Now, To provide you that illustration, I'm going to use the data here. That is the data that I'm going to use. Okay, so now this is the data we had put up earlier on sales, calls, and copiers sold. So copiers sold is the dependent variable, and the number of sales is the independent variable. This is the data here. I'm going to go through the process that generates this order table, because this is the table that enables you to do the estimation. And before I go on, let me say that next week I'm going to use SPSS to do this estimation. I'm just trying to explain to you what the process that by which we do the estimation using the formula that we have here. I think mislocated the formula. Okay. All right. This formula, I'm going to implement it. Okay. So for now, I'm going to stop share and go through that formula. But as you can see, in order to implement this estimation, you must find X bar, you must find Y bar. Okay. So let us see if we can implement the model. Okay. And the model is implemented here. As you can see, you calculate Y minus Y bar. See here, the formula says summation of X times X bar times Y minus Y bar. So you must have Y minus Y bar, X minus X bar, and then you must have Y minus Y bar times X minus X bar. You get the sums, but I will implement it right here before you. So I'm going to stop share here for a minute and pull up an Excel file. I'll pull up an Excel file. Share to the Excel file. All right. So it's easy to illustrate. Now, what we're going to do next week, we're going to use SPSS to implement this, and you can see how easy it is, because I want to be able to illustrate both simple and multiple regression on SPSS. But for now, you need to understand the process that goes on, the formula that SPSS uses, and the formula that you will probably be using in the future if you take additional courses in statistics, where you learn the theoretical foundations of regression analysis at a much higher level. So in order to get Y minus Y bar, you must first of all get Y bar, which is the mean. Here you have the average of Y. Here you have the average of X, all right? And they are located in location in row 20. And so Y minus Y bar will be equals C5 minus $C $20. And then you can drag it down. find out that if you take the sum, you get a 0. So the sum of y minus y bar is equal to 0. You do the same there. Equals D5 minus $D, $20, and you drag it down. And you get a 0, and so you know that your calculations are correct. And so now we have to then calculate y minus y bar times x minus x bar. X minus x bar to the power 2 there. All right, so y minus y bar times x minus x bar will be very simple. Equals E5 times F5, E5 times F5. Okay. And here will be x minus x bar squared equals 5 to the power 2. Right? And so that gives you the same results as you saw on the screen earlier. All right, so now that we have these numbers, if you can write them down, we can verify what we're doing. All right, so you can see here that the summation of y minus y bar times x minus x bar, you can see their summations very clearly. The summation y minus y bar times x minus x bar is 6672, and the summation x minus x bar to the power 2 is 25600. So now I'm going to stop share this. And get back to our regression model. Okay, so as you can see here, that the summation y minus y bar times x minus x bar is 6672, which we obtained over there. And the summation of x minus x bar to the power 2 is 25,600. So we apply them on this formula. As you can see, we have 6672 divided by 25,600, which gives us 0.2606. Okay? And so we have B hat. Okay? We have B hat. .2606. Okay. This is what we had over there. Okay. So this is our estimate of the slope of the line. This is y equals a plus b x plus e. So here our estimate of b is 0.2606. Okay. And we will explain that later. And then over here, we estimate a hat, okay, to be 19.98. I think we have it somewhere there. Okay, so we estimate a hat to be, as you can see, a hat is y bar minus b hat times x bar, and y bar is 45, x bar is 96, and so a hat is 45 minus 0.2606 times 96, which is 19.98. All right. So now what do we have? We have what we call a model equation. The model equation simply says that the amount of sales that a salesperson makes is 19.98. So approximately to say a salesperson, let us assume some kind of organizing where the salesperson just sits on their desk and people come in to buy copiers, and then they go and explain the copier to them. And so without making any sales call, the salesman is going to be able to make some sales, which is approximately 20 copiers, approximately 20 copiers. Now, if the salesperson makes calls to businesses or to individuals or whatever calls that they make, for each additional call, they sell 1/4 of a copier. Of course, we know there's no such thing as 1/4 of a copier, but it simply means that by the time they make 4 calls, they will be able to sell 1 additional copy. This is what it is. Okay? So what is the estimated sales, excuse me, for a salesperson that makes 30 calls? This is how we use the regression model to estimate, to predict the number of sales copiers that a salesperson will make. Okay, so the estimated sales for a salesperson that makes 30 calls will be equals to 19.98 plus 0.2606 times 30. So we estimate that that person will sell between 27 and 28 copies because they made 30 calls. So S of 30 will be 27.77, which is between 27 and 28. They might sell 27, they might sell 28. More likely they will sell 28 than sell 27, but some will get 27 out of it and some will get 28 out of it. All right. So what we call this is a model equation. Okay. The model equation is y is equal to 19.98. This is a model equation. now I'm going to take this out. Okay. Okay. All right. Like I said earlier, simply say that if sales call increases by 1, the salesperson will increase sales by 0.26, which implies that about 4 sales calls will bag 1 additional sale. This is what we are saying. So this is the model equation that predicts the number of all right. The number of copiers that will be sold depending on the number of calls that are made. Now we have to go beyond this stage, okay? The next stage of our discussion is to ask ourselves, how strong is this relationship? Essentially, what it simply says is, to what extent does the number of calls explain the number of copiers sold? To what extent? Because now think about it. A salesperson that is making calls and expecting to generate sales might depend, first of all, on whether the customer actually needs, what do you call it, a copier. That is the customer that is being called. Do they need a copier? This is number one. Number two, do they have the ability to pay for a copier? Three, think about the personality of the salesperson. Somebody might be good at talking people into buying what they're proposing to sell. Somebody might not be that good. Some salespeople will be better at it. Others will not be just as good. And so we ask ourselves, how strong is the relationship? To what extent does sales call alone explain the number of copiers that are sold? All right. So we calculate what is called a coefficient of determination. And again, I'm going to post for you a complete solution that has all that. But you can see we are using exactly the same formula, except that at the bottom here, we are using summation y minus y bar squared. And so we can go and look at that if we want to. But I just explained to you how the formula is derived. And so we find out that 74.6% of sales is explained by the number of sales calls. So there is 25%, 25.4% that is not explained by sales calls. That could be the result of other factors, like the personality of the salesperson, the needs of the customers, their preferences, and the capability of the customers. These are other factors that weigh into it. And so sales calls alone do not explain 100% of the sales that are made. All right. Now, the next thing is to ask ourselves, well, we have gone through an estimation process. Remember, this is an estimation. We simply estimate, we simply assume there's a relationship between sales calls and the number of sales, the number of copiers that are sold. But we also want to test the significance of the slope. That is to say, does the sales calls significantly affect sales? Okay. Now, remember, we are just talking about sales here. Then there are other relationships that where we try to ask ourselves, we don't know a priori whether there's a real relationship, okay? And so we try to test the hypothesis whether the independent variable significantly affects the dependent variable, okay? There are situations where that doesn't exist, okay? So we have to go and test the hypothesis. So this is going to be hypothesis testing for linear regression. So how do we test the hypothesis for linear regression? So we have the model, and I'm going to write out the model again. Y is equal to A plus B X plus E, okay? So we want to test the hypothesis, and the whole hypothesis, the hypothesis is to test whether B is equal to 0, okay? The null hypothesis is that B is equal to 0. And so I'm going to put this way. Okay. This is the process of hypothesis testing for a regression model. All right. So our hypothesis, quite simply, is that B is equal to 0. That is our null hypothesis. Okay. Our null hypothesis, or the way we begin the process, is to state the null and alternate hypothesis. This is the alternate hypothesis. This is the alternate hypothesis, and it is simply that B is equal to 0. There is no relationship between sales calls and the number of copies that are sold. That is the null hypothesis, okay? And the alternate hypothesis is that B is not 0. That is to say that the slope of the equation is not 0, that sales calls significantly affect the performance of the salesperson, okay? So that is how we state the null hypothesis. And the process is that we estimate B hat, and we find the standard error of B hat. And we, okay, so this is how we find the standard error of B hat. Excuse me. This is the table. So we'll go through the table as we did it for estimation of B hat, okay? But then you have the formula here. The standard error of B hat is estimated using the equation that you see here, okay? Now, after we state the null hypothesis, okay, after we state the null hypothesis, we estimate, of course, B hat, which we have done, and then we estimate the standard error of B hat, and we calculate Z, which is B hat minus the null hypothesis, and I'm going to change that to null hypothesis, okay? And divide that by the standard error of B hat. The decision rule is that if Z is greater than Z star, we reject the null hypothesis. So this is a table that we create, and we create it exactly the way we did the other one. All right. Let us see here. We find out from our hypothesis test that our critical Z is 2.33 because our level of significance is 0.01 and the critical Z is 2.33. And based on our calculation, we find out that Z is 2.86, and therefore we reject the null hypothesis that B is equal to 0. Now, once we reject the null hypothesis that there is no relationship, then we conclude that sales calls significantly affect sales performance. Sales calls significantly affect sales performance. I have other examples. For example, this is called the dividend policy model, which actually argues or tries to ask the question, if a company pays dividends, does it affect the price per share of the company? Okay, this is another example, and I'm going to post this for you to see and to practice on it. There's another example here, which is called the Buena School Bus Maintenance model. And so, does the cost of maintaining a bus depend on the age of the bus? Okay. Does the cost of maintenance for a bus depend on the age of the bus? And so, A is the fixed cost, the minimal cost, even when not used, that is, even when the bus is not used. And B is the additional cost per additional year of use of the bus. Okay. The data is here. I'm going to, again, post this for you to see. All right. And here we use our model to estimate the cost of maintaining a bus that is 8 years old. And we find out that it will be $454 per year if the bus is 8 years old. Okay. And so, what is the cost of maintaining a bus that is 9 years old? You see that it is 476. And I have, several examples here for you to look at when I post this. And the process of, testing hypotheses for each of those examples. Now, the final thing that I'm going to talk about is looking at an SPSS printout, which I'm going to illustrate next week before we get into regression analysis. Okay, and the model here is about the cost of food, the expenditure on food, and family size. If you look at this, you will see here that we estimate R squared, which is to say family size explains 76% of expenditure on food. And you can see the Z value here. Like I said, SPSS, we print everything as is a T, even though it says Z. And so the slope is 0.414. That is, for each additional person in the family, 41.4 cents is spent on food. But then every family will spend about, well, this is in thousands anyway. So about $3,000 or $300 worth of food, worth of money on food, and the Z is 17. So the Z is 17, and so we do not reject the null hypothesis of a constant value for that expenditure. And here we also do not reject the null hypothesis. So family size significantly affects the amount of money that is spent on food. So I'm going to post all of this, and then when we come back next week, we are going to illustrate how to do this on SPSS, okay? So I don't have my SPSS, I don't have access to my SPSS here, so I will not be able to do that illustration for you. Okay, does anybody have any questions? Hello? All right, now, hearing no questions, I'm going to make an announcement. Just a minute. The announcement that I'm going to make is that in place of your projects, I'm going to post a number of data sets. I'll give you this instruction in writing. I'm going to post a number of data sets. You can also generate your own data set, but you use my data sets to you select variables in my data set and set up a hypothesis and explain what a hypothesis is, test it, create necessary tables, and submit that as your final project. You may use SPSS because the data sets will be both in SPSS and in Excel. So you can use SPSS, you can use Excel, whatever software that you have, you can use it, provided that your results are very clear and properly presented. I will post them before this weekend is out. By Sunday, you will see all the data sets. I will make an announcement. I will provide instructions, and I will take note of those who attended today, and create a record of attendance. As I explained to you, I spoke with the chairperson, and the chairperson advised that I make attendance also part of your grade. All right, so any other questions? All right, hearing none, the class is dismissed. Thank you very much for coming.
Thank you, Professor.
All right.
Thank you, Professor. Have a good day.
Have a nice day.
Yeah.